This doesn't make any sense. November either has 30 days or 30.0416 repeating days. Hello and welcome to Senior Code Review Buddy. My name is Chris, and today I'm going to talk about daylight savings and the annoying impact it can have on your code. Now, if you live in a part of the world that doesn't take part in daylight savings, first of all, I'm jealous. The short version is that twice a year we'll adjust our clocks by an hour. Time moves back an hour in the fall and forward an hour in the spring. This means that 1 to 2 a.m. happens twice one day in the fall, and one day in spring the clocks go directly from 1:59 a.m. to 3 a.m., skipping the whole 2 a.m. time. In my opinion, this generates a lot of unnecessary challenges and annoyances for people impacted by the world, like scheduling international meetings when people live in different time zones that either don't have daylight savings or have it, but have it at different times. But as annoyed as I am with all of that, today I'll try and focus on just the coding problems that it can generate. Since in time zones with daylight savings, we can either repeat an hour or skip an hour, we can get some weird data. Now, I live in the Eastern time zone, which does have daylight savings, and as you'd expect, it takes 24 hours to get from noon one day to noon the next, other than the twice a year when it's either 23 hours or 25 hours because of that time jump. And if my code is working in the Eastern time zone, it'll maybe take that into account. Maybe, I think, hopefully. But what exactly this looks like might not be what you or I generally expect. Now, these examples are going to be in Python, but I think most languages might have some weirdness around this as well. So with that, let's go take a look at some examples. So I've got this little code snippet here to show how Python deals with datetime values around daylight savings. So we start with a datetime in the Eastern time zone. It's 11:15 on November 2nd, so it's just a few hours before daylight savings change happens for the fall. And then we take that value, we make a copy of it with the UTC time zone, which doesn't have daylight savings. And then I've got just a small little loop here that just goes over some hour intervals, just adds the same time delta to both of these times, prints out what the new times are, and prints if the values are still equal. Now, are there any guesses on what this code's going to do? If we start with two values that are equal, which we do here, and we are adding a constant, the same value to both of them, which we do here, I think it's safe to say that generally speaking, we'd expect them to stay equal the whole time. If I run the code, when the values are 0 hours, still true, 1 hour, still equal, 2 hours, not equal, 3, 4, and 24 hours, not equal. That doesn't really make sense. But if you dig into it, it maybe still doesn't make sense, but I understand why Python does it. So there's two different reasons we're dealing with here. So for the first case, this one here, if we look at it, we haven't had the impact of the daylight savings change yet. So these should be the same times they were an hour before. We just add an hour to both of them. They're the same time zones. So what happens? Well, Python says that because this is between 1 o'clock and 2 o'clock on the day where the time repeats that interval, this is sort of called the repeated time period. And Python says that during this time frame, this date time can never equal another date time. That's in another time zone. So this will always be false, even though these are the same time. Don't really know why it does this one, but that's a thing that Python does. And then if we go to the case of 3 hours, 4 hours, and 24 hours, well, we can sort of see that it's an hour later from 2 to 3 hours, but the time zone's also changed because the daylight savings. So this isn't a 1 hour jump. Instead, it's a 2 hour jump. So because we added an hour for daylight savings and we added an hour because we actually moved an hour ahead. So that extra hour got silently added in here. So yeah, it's not going to be the same as what the UTC time is. So things just don't work. Yeah, and then it kind of makes sense why it doesn't enable UTC stuff, because there's no magic hour suddenly added here. So yeah, depending on what time zone you're using and how you're doing things, you might get slightly unexpected behavior around daylight savings time. And so if instead of using Eastern time, we used another time zone that didn't have daylight savings, like Tokyo, these values would always be equal. It's just because we're using one that has daylight savings and it's around daylight savings time. So in a practical sense, what kind of problems could this cause? Well, what if you have a monitoring system and you want to make sure that some process generates no more than, the same amount of errors that it generated yesterday within some tolerance of like 0.5%. Well, if we're basing it on days and we're using the Eastern time zone, well, there might be a day where that day is actually now 25 hours instead of 24 hours, which means even if you're just producing errors at the same rate per hour, that day is going to have about 4% more errors, and it's going to look like there is an uptick that actually isn't real. It's just your day was longer. So there's a problem there. So my advice, and it's the main advice I will give basically anytime you're working with time, try to use UTC as much as possible. If you do that everywhere, you don't have to worry about daylight savings. It makes things a lot easier. You really should only use another time zone if it's at the end of a stage and it's how a user wants data to be seen, then it's okay, but try to always save data in UTC, don't save in local time. And with that, let's take a look again at that first bug I showed in the beginning around the number of days in November. With the knowledge from that example we've just went through, I'm hoping the issue here is a little clearer now. So let's run the code again and see what we get. So we get days is either 30 days in November or 30.04166666. Okay, so how this sort of happens is I've not been clear to Python about what time zones we should be using. I don't specify them here. So Python defaults to using my system's time zone, which for me is Eastern time. So then when we have our first computation here, we take December 1st Eastern minus November 1st Eastern, and Python sees that they're in the same time zone, so it just ignores time zone, and it just does a basic simple subtraction, and it gets 30 days. So when we divide that, that's how we get exactly 30, which is what I think everyone would say is the correct number of days in November. But technically, when you have daylight savings, November does last a little bit longer. There is that extra hour in the month, which is why when we use timestamps, we actually get that. Because the reason, sort of how these timestamps work is what is this time compared to January 1st, midnight, 1970 in UTC time. So because we use UTC as a comparison for both these, the magic hour that gets added by daylight savings doesn't disappear. It's included in that because in terms of just seconds that pass from November 1st to December 1st, it's not 30 days worth of seconds. It's 30 days worth of seconds plus an hour. And so that's why we get this difference here. So what's the fix? Well, I think it depends exactly on what you're trying to do. If you are trying to figure out in terms of, seconds or minutes that are happening in November, this timestamp route is what you want to do. It does make sense to have your current time zone and do the subtraction like this. This is the correct answer, I think, in that situation. But most of the time, and I think in almost any case, you probably actually want the number of days in November to be 30. So what I would suggest doing in cases like that is actually just tell Python what time zone you want to use. And I would recommend using UTC, because when we use UTC, we don't have to worry about daylight savings. And if we do that, I need to import it. And when we have that, now we get 30 days, both of them correct. So once again, try and use UTC when you can. It'll help you avoid weird issues like this. So I've got one more example now. So this example is a bit bigger, but we don't have to worry about most of the details here. They kind of don't matter. Basically, what we've got here is we've got a class called order, It starts by taking an order number and an order time, and then at some point in the future, it will have payment received called to add the time that happens, and order shipped called to have the time that happens. And then there's just a little status function that just prints what the status of the order is. And I've got a small little flow here at the end, just sort of using this in a basic flow and showing what happens. And one thing I'll point out is that status, I've made it such that, for user convenience, they can specify what time zone they would like to see the date times in. So in our little example, we start with an order time. We use UTC here because we've been bitten by that so much. Add the order time, and then 4 minutes later, we get the payment. And then 8 minutes after the order is made, we ship the results out. That seems good. And we print our status each time. And then we'll say someone else from a different location says, oh, I would like to see these results. So they look at it. And that's where things get a little messy. So let's run this. We can see that looks good. Yep. 5:55 it gets the order. Yep. 5:55 gets the order. 5:59 gets payment. Then 6:03 gets shipped out. And then this is where it's printed in Eastern time. 1:55 we get the order. 1:59 we get payment. 1:03 we ship it out. So if you just look at this obviously looks wrong. This looks like you're shipping it out before you've received payment and before the order was even made. And if you see this makes you think, okay, are we writing the wrong data to the wrong orders? Are we something's happening and we're shipping orders way out of order? This would be concerning to see. But because of how this example goes and what we've seen, we know that this 1:59 is 5:59 UTC, and this 1:03 is 6:03 UTC. So we're not actually shipping things out of order or doing anything wrong. We don't need to panic. But what's happening here is if you look, so the daylight savings for this time zone happen here, but there's no information that we're printing here to indicate what the time zone is, which would help the user know that, oh, it's because of daylight savings. And that's because we printed this specified string here and we didn't include that, which is easy enough to include with a %z. And if we run that now, okay, yeah, we can see this was at -4, -4, -5. So, okay, yep, that's right. That's actually 4 minutes after that. That's not before it. So no need to panic. So this time we weren't doing anything wrong with the data per se, but in how we were displaying it, we weren't including time zones, which can have an impact in how things look at times like this. So just keep in mind that issues around time zones and daylight savings, it's not necessarily going to be bugs in like wrong data, but it can just be you're displaying something and missing some information that generally doesn't matter, but sometimes matters a lot. So there you go. Just a few examples of how daylight savings can cause unexpected issues in your code. And if there's one thing you take away from this video, I hope that you should try and use UTC whenever you can with time. It will make your life easier, trust me. And if you go to work after a daylight savings event and there was a weird test failure or flake all of a sudden, maybe look into it. Maybe it was something around daylight savings. If you've enjoyed this video, please consider hitting the like button below and subscribing. If you have any comments, code you'd like me to review, or ideas you'd like me to talk about, please leave a comment below or reach me at chris@seniorcodereviewbuddy.com. Thanks, and have a great day.